So, we've learned about binomial theorem. This is binomial distribution, really binomial probability distribution. Okay, so it does have some similarities. You need to be binomial theorem first, or it certainly helps. But they are different things. So sometimes you hear the word binomial and you think, oh, that's the same thing. Theorem, distribution, thing. It isn't quite the same. This is representing, this is really calculating more probabilities. Specific case here is calculating probabilities for an experiment where there's only a success can happen or a failure. Okay? So sometimes we call it a hit and a miss. So there's the binomial, two things. It can happen or it cannot happen. There's no in between. Okay? So, and you have a number of trials, and you're trying to figure out the probability of maybe out of 10 times you perform this, it's going to happen 6 times, or more than 6 times, or 0 times, that kind of thing. So, many actions have only 2 possible outcomes. A tossed coin comes up heads or tails, a hit or a miss. Pardon me? Yeah, we don't include that. Yeah, we're not going to. That is not a binomial distribution. Okay. Binomial experiment has a fixed number of independent trials in which there are exactly 2 outcomes. These 2 outcomes can be classified as a success or a failure. A list of possible outcomes and the associated probability is called a probability distribution. We actually did probability distributions back in, I guess it was 2019 in the stats unit. We graphed them, so we'll do one graph here, but really we're not going to graph one. So a probability distribution of a binomial experiment is called a binomial distribution. So we're going to do the first one the long way with a tree diagram. So under good conditions, a particular archer can hit the bullseye 75% of the time. The archer shoots 3 arrows. Complete the probability tree below to show the different possible outcomes of her 3 trials. The letter H represents a hit and the letter M represents a miss. So, probability that she hits the bullseye is 75%. I'm going to use decimal form, okay, but you could use percent. When we put it into a calculation, we're going to convert it back to decimal or fraction. Okay? Not dependent every time she tries to hit the bullseye, that's the probability. So the next time she takes a shot, it's a hit or a miss. If she hit it the first time, if she missed the first time, it's a hit or miss the second time. And then the third time, same thing. Okay, so underneath is a chart where we're going to show all the possible outcomes that could happen. So you can see part of it's filled in for you. The first one could be a hit, second one a hit, third one a hit. Okay, that's really the top set of branches there. Okay, H. So the probability of that happening is 0.75 2. Okay? If you show it in simplified form. Second one that we've listed here is a hit, then a hit, then a miss. So it's really the second set of branches. So just to help, this is going to help us later. How many hits are in that set of branches? 2 hits. So what happens, 0.75 times 0.75 times 0.25, and we can simplify that, 0.75 squared. Then a hit, a miss, a hit. So basically we're just going down the chart. So I'll give you a couple minutes to fill in that chart from the tree diagram. Okay, so taking a look here, I just abbreviated H and M for the minute. In these, I kept the 0.75s at the beginning. So that had to be 2 squared, one of them. But you'll notice there's a total, you think about it as the 3 sort of, 3, because there's 3 events happening 3 times. So you take a shot at it. And so we're going to summarize in the chart on the right-hand side. You'll notice that this one is the same as this, is the same as this. This one is the same as this, is the same as this. And then these are different. Okay? So to summarize in the next chart, let me just split the screen here. Okay, so we can summarize because there's common. So when there's 1 hit, that's when we have 0.75Q. Okay, 3 hits, I should say. Only one way of getting that, 0.75Q. 2 hits, there are 3 ways of getting that. So that's this, and this one. Okay. Oh, that's really nice. One sec. Now I've lost my mouse. Oh, this is fun. Okay, so then 1 hit, these ones here, 3 ways of getting those, and that's 0.75 times 0.25. I don't know. Seems in the afternoon it gets tired because it was really good this morning. Anyway, so there's going to be 3 of those. And 0 hits, there's just the one way of getting that. Probability is 0.25 cubed. 1 times 0.25 cubed. Okay, and then probability in decimal form. So entering those into your calculator. Okay. I'm not going to, you can do that on your own time. I'm just going to give you the values at the same time. Okay, rounded to 2 decimal places, 0.42. Second one, 0.42 as well, because 3 times 0.25 is 0.75. Then 0.14, then 0.02. Okay. Now, if you add those together, you get 0.84, 0.98, and 1. You add those in your head, So total probability distribution is 1 for an experiment. Makes sense, right? So, probability histogram, we did some of these last year. So this one, our labels for 0 hits, that's 0.02. So, about there, just a little bit above. Then for 1 hit, that's 0.14. So, about there. And then for 2 hits, 0.42. And goes all the way across, actually. Go on. Okay. So, total area of the bars, so they're each 1 in width, so the total area will be 1. We already added these up, right? So, use your knowledge of the binomial theorem to expand this. So, consider it just a binomial cube, happens to have variables h and m, not the sort. First express all the coefficients in the form NCK, and then write the expansion evaluating those. Go back to here. So remember, good practice. So exponent there is 3, so that's going to be 3C0 H cubed m to the 0, so you don't have to show it, plus 3C1 H squared m plus 3C2 H m squared. And last one is 3C3 m cubed. Okay, that's the binomial theorem for that particular binomial, h plus m cubed. Now evaluate the coefficients. 3C1 is just going to be 1. That's right, 3C0 is going to be 1. 3C1 is going to be 3. 3C2 is going to be 3. And 3C3 is just 1. So, in the expansion from question 6, substitute 0.75 for H and 0.25 for M, but don't simplify. So this would be, so H is 0.75. You should start to recognize some similarities. Okay, so what do you notice about your answer and the second last column in the table? So if you look back up here, you'll notice 0.75 cubed, we have it. 3 times 0.75 squared times 0.25, we have it. 3 times 0.75 times 0.25 squared, we have it. And 0.25 cubed. okay, is exactly the same. Okay, so what do you notice? The same. All right, so from question 7, you should have seen the probability of getting 2 hits and 1 miss. Okay, so 2 hits and 1 miss is 3C1, 0.75 squared times 0.25. Notice this is exactly the same as 3C2, 0.75 squared, 0.25. 2 hits, 3C2. So 3 trials, 2 hits. The values are exactly the same of 3C1 and 3C2. So this is where, slightly different in sense of ordering, but your R value, or sometimes called K, is the number of successes that you want. Okay, N is the total number times your trials, total number of attempts. C is the number of hits, or sorry, K is. So let's say the archer took 10 shots, write an expression, 10 shots, write an expression for the probability of getting 4 hits, and therefore also 6 misses in 10 trials. So now we have 10, and that K value is going to be the number of successes or hits, 4. Normally, the exponent on that first term in your binomial is 10 minus 4, right? But because 10C4 is the same as 10C6, we're switching this to make it 50. Okay, so then the probability of a hit is 0.75, all right? And that's going to be the 4. Okay, you got 4 hits. You have to have 0.75 to be exponent of 4 in that expression. So back at your table of values. 0.75 for every success. Here we're told we have 4 successes, 4 hits, so we need to have an exponent of 4. Okay, then the misses will be 0.25 to the 6. Okay, so now to get that, okay, that's the difference of these. So really, back in binomial theorem, when we're expanding a binomial, the first term was raised to the exponent, the difference of these. Okay, so now the exponents are switched around. That's the only difference between. Okay, so suppose the archer attempts N shots or trials, where capital H is the probability of hit, capital M probability of a miss. Write an expression for the probability of having lowercase h hits in N trials. So this is your general binomial probability distribution formula. So N, C, lowercase h, total number of trials, number of times you get a success, probability of that success, to 8. Right? H just have to go together. Those are the hits, the successes. Okay, and then the misses will be N minus H. Sometimes capital H is just lowercase p for probability, and the complement of that, not a miss, is p. So just be aware, sometimes those values are used. Okay, so let's try one. Use your formula to determine the probability of getting 10 hits in 15 trials for an experiment where the probability of a hit is 0.6 and the miss is 0.4. Sometimes they'll just give you the probability of success. You have to calculate probability of a miss, 1 minus it, right? So 15 trials, the 10 hits. Probability of a hit and a miss.
Sounds like that. Is he using some serious stuff?
Okay, so doesn't say what to round to. Let's go to 2 decimal places. 0.186. Okay, so some notation to be aware of. So a binomial experiment. So X, capital X there is a discrete random variable. So this is for probabilities. X follows this B tells you it's a binomial distribution. The first value that's in there will be the number of possible trials, and P will be the probability of a success. And then you have to be told, okay, how many successes do you want? Well, you have to be told those two values, and then how many successes you want to calculate. So again, binomial experiment has 2 outcomes, a success or a failure. Again, lowercase p is probability of success. Lowercase q is probability of failure. Those are sort of standard. Probability of having k successes in n trials. Notice the little bit different notation there with C. So IB could also use where the n is in the upper left. So just be aware of that. Okay, so I'm not sure it's used in Europe, different places. It means the same thing. Okay. Okay, so just be aware of that. You will get a data booklet for your IB exams, so it'll be in there. Okay, so let's do some calculations. You'll notice on the right-hand side of the note, tells you how to use the calculator. We're kind of going to do it at the same time. We'll do the first one the long way. So determine the following probabilities, and the answers are given, but we'll work on them. What is the probability of correctly guessing the outcome exactly once out of 4 rolls of a die? Okay. All right, so we have 4 rolls. And I'm going to use, just because it's so common for us, the C notation with the long subscript. Okay, correctly guessing what's going to be, so that's once. Exactly once out of 4 rolls. And this is for a regular 6-sided die. Okay, so if I'm correctly guessing it, there's 6 possible options, so my probability of getting it correct is 1/6. component 1. Probability of getting it incorrect is 5/6, and that could happen 3 times. Okay. The probability of guessing it correctly once out of the 4 times. So enter that in the calculator. So 4C1 is 4. You don't really have to bother using this notation. We can use fractions. You don't have to. We'll go to 4 decimal places like the answers that are given there. Now, that's sort of the algebra, that is the algebraic method of doing it. Still need your calculator in order to, in most cases, we're not going to ask you to do that by hand, even though the fraction is good. Within your calculator, just like last year we did normal distribution, remember that probability we did in that 20? In that distribution, so if you go second vars, and you can see the normal there that we used last year, cursor up or cursor all the way. Oh, oh, there it is. Sorry, I missed it. There's some extras that I found on the other calculator. So, you cursor up, you'll see binom PDF and binom CDF. Okay? So, binom means binomial distribution. Okay? Function. The C is cumulative. So that means if you're finding 0, 1, 2, that's cumulative. You can get the calculator to do it a little bit faster than doing it separately. If we have a question where it's exactly once, or exactly 2 times, or exactly 3 times, we use the PDF. Not quite sure actually what the P means in difference, but the C is cumulative. But, maybe it just means probability distribution function for 1 value. In any case, enter on that. Most of you will have this where it prompts you. A couple of you have a little bit older calculators where it doesn't prompt you. You have to open the brackets if it doesn't open it. Enter in the number of trials, so in this case 4. So some of you will open the bracket there and put 4. Okay, then P, so enter on that, probability is 1/6. Okay, so here this would be comma 1/6. And X value, X is how many successes you want. In this case, we want exactly 1. So this is for an older version of the calculator. So I think you folks out there have an older version. Right, Kristen? So, you want to try this, right? Oh, you got a newer version. Oh, okay. Perfect. Okay, so enter on that. There you can see it. Enter on that. And you get the same value. Okay. If you were to do this, this won't be on your test this week. But say your IB exam, very rarely do they say that you have to do it. Like, I haven't seen where they say you have to use the algebraic method. But if you're using your calculator, you want to write out what entries you put in there. Right? Whatever you get when you press paste on that, it shows you. Okay. Okay, true or false test has 10 questions. Suppose all questions are answered by random guessing. Determine the probability of obtaining 7, 8, or 9 correct answers. Okay, so this, I'm sorry. So this is the probability of exactly 7, exactly 8, exactly 9. So that's 3 calculations, okay, that you have to either show the long work for, or 3 calculations of binomial PDF, but there's a faster way of doing that within one binomial PDF. So I'm going to just show out the long way. So, and then we'll calculate it using our calculator. So, 10 questions. And getting 7 correct. True or false, the probability is 0.5 or 1/2. 7 correct. And same probability for incorrect. So really, all of these, you could simplify this to 0.5 to the exponent 10. Okay, that's 7 correct. 8 correct. So really, I can just do that, right? Because these probabilities are exactly the same. So 7 plus 3 is 10, 8 plus 2 is 10, and then my last would be 10 to 9, 0.5. Okay. So really, in terms of entering that in your calculator, you can factor out 0.5 to the 10, open bracket, 10C7 plus 10C8 plus 10C9, get the answer. Maybe I'll show that. Okay. So. Okay, so you can do that in your calculator if you want. Or take a look at what we can do with binomial PDF. So distribution. Nope, can't do CDF. Well, maybe we can in the newer calculators. Let's just check it out. So one way, I'll show you the first way. Binomial PDF. 10 trials. Probability is 1 divided by 2, or 50%, or 0.5. And then here, you can, for this version of the calculator, I think we still need the squiggly brackets. So second bracket is the squiggly bracket. And we're going to enter 7, 8, 9. Close the squiggly bracket. If it doesn't like those, we'll get rid of them. Okay. Yeah, I think it does, because that's how in the older version of the calculator you want to show it. So that means when we enter here, you're actually going to get the 3 separate calculations. What this would be, that would be, that would be. Okay? You can sum those. You don't have to copy them out, add them together. What you can do is, let me look here, it's a list of values. So go second, stat, and we're going to go to math. So often we go to math here, we're going to a different math, and you'll see sum. Okay, so you can do that for a list. Say you had entered values in L1, you can go, in this case, that's why it's called list. The first screen was L1, L2, so you can find the min, the max, the mean, median, sum. We used to, last semester, we just did one variable stats, and it gave us all of those values together from our list. But in this case, we don't have it in a list. So we're going to enter on that, and then answer, close brackets, and it should give you the answer. Okay? Now, let's take a look at the newer version of the calculator. Just let me see here. So distribution, binomial CDF, kind of was back to like normal distribution. It always started from 0 to that value. So if we have 10 here, I don't think we're going to be able to.
Try like putting it in as like min and max. I don't know. That can work. Probably not though.
Well, what do you mean? 7 here, comma.
I don't know.
Yeah, I don't think it's going to be able to do it either. I thought maybe you could do the continuous between those, maybe in this new version of the calculator, but I don't think you can. Okay, so we'll keep it to the other way. 0.170. Okay, so the next one is where we'll use the cumulative distribution. So it says a multiple choice test has 12 questions, and each question has 4 possible answers that you get on your test. If all the questions are answered randomly by guessing, so if you were to just go, oh, I'm going to do it, not even look at the question, A, B, A, B, C, just eeny, meeny, miny, determine the probability of obtaining at most 2 correct answers. Okay, probably, you should probably do this for at most 6. You get a pass in the point, right? But in any case, so really, in this case, at most 2 correct would be 0 correct, 1 correct, 2 correct. So still 3 calculations, not terrible.
Wait, hold on. 12 questions. That's how many questions we put on our question, right? Wow.
20.
Oh, 20.
Or 22, actually. Okay. So, in this case, let's just do this by our calculator. So second large distribution, but choose binomial CDF. Number of trials 12. Probability is 1 out of 4 or 0.25. Here your X value is your maximum. Maximum of 2 correct answers. So it's going to go from 0 to 2. Okay, so we put 2 there for the maximum. Okay, so here, this is 12, 4, 2. So that's going to be the same as binomial CDF. I'm going to let it go away. Okay, and then adding those together. Or the algebraic method. 0, 1, 2. Okay, and you get the answer that's there. Okay, take a look at D. The right-hand side, a manufacturer of a gas generator estimates that 0.1% of the generators are defective. If a customer places an order for 25 generators, what's the probability that at least 2 of them are defective? Okay, so now you might want to consider, like, even though defective is not good, that's really what we're looking for. So that's kind of our success in being defective, even though you don't want something to be defective. You still want to calculate that. Okay, so Where's the probability of at least two of them? So now, the thing with this is, if we do it the long way, we have to go 2 defective, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 25. You do not want to do that. You don't even want to list those in Binomial. This is where you would use the complement. What's the complement of at least 2 being defective? 0 and 1, right? So you could do 1 minus the probability of 0 defective minus the probability of 1. Or in it a little bit faster, 1 minus, and again, we'll use our calculator.
Everyone noticing little pink dots happening?
Yeah, I have, but I can't stop it. CDF of, okay, 25. Being defective is our fix. We don't want a percent in this, so that's, convert that to a percent is 0, to a decimal without a percent sign, divide by 100. And then we want to go, we're subtracting 0 to 1. So our maximum, because we're doing PDF, right? That's going to be 1 now. Oh, let's do this. 1 minus. And 1 minus that. Oh. You already did the 1 minus. Oh, I already did the 1 minus. Thank you.
You need to try and, is there a way to, like, no, I mean, you need to, consolidate it?
I don't know. I'm not worried about it now. Okay, so that is binomial probability distribution. So then, turn over. We're just going to do a little bit more. And then we'll be done. Okay, so we talked about standard deviation last year as well, right? And varies a little bit. Tends to be in most of, like, especially in science, probably I think talk about standard deviation a fair bit. Variance, can you talk about variance very much? I mean, it's just a square of the standard deviation. It's just, again, a measure of the spread of the data. Seems to be an idea that they tend to talk about variance a little bit more, but you know the standard deviation, you just square it, you get the variance. The variance, you root it, you get the standard deviation. So, it's a comparative value, right? Like you have to know the mean and your standard deviation and variance. Using back to last year, we know the distribution and stuff like that. Okay, so the mean is sometimes called the expected value, which kind of makes more sense. What's the expected number of times you're going to get a bullseye, right? That is more how in non-math world we would actually say it. A mean number of times kind of makes sense. On average, how many times mean on average. But because you haven't actually maybe done the experiment, expected value kind of makes sense to me. So it is a weighted average of the possible values that X can take, each value being weighted according to the probability of the event. Okay, so the expected value of a certain event is the number of trials that you take and the probability of having that success. That's your expected value or average number that you want to get if you perform the experiment over and over and over and over again. The variance measures how far a set of random numbers is spread out from their average value. It is the expectation of the squared deviation of the random variable from its mean. Okay, so standard deviation is that lowercase sigma. Hope at the back. And so it's the square root of the variance. Okay. So the variance is the square of the standard deviation. Okay. If it's a binomial distribution, you can calculate. You don't really need your calculator other than enter the value. You can get the variance by multiplying this expected value by the probability of a miss or a failure. Okay, so expected value is n times p, variance is n times p times p. That's really all that it is. Those formulas are in your book. So, question 15, a biased dice. That means maybe it's weighted. Okay, it's not just an equal chance of getting a 1, a 2, a 3, a 4, a 5, a 6. So if you have a biased dice and it's thrown 50 times, and the number of sixes that you get is 12, if the dice is thrown a further 12 times, find the probability that a 6 will occur exactly twice. Okay, so that's a binomial distribution. Okay, so it's either going to be a 6 or not a 6. So the long way, or the algebraic way, so another further 12 times. Twice. You get a 6. So this is where we have to calculate our probability. 12 out of 50. Okay, so that's the probability that we'll get a 6 with this biased dice. You can reduce that if you want. You want it to occur exactly twice, so that's squared. And then the probability of not getting a 6 would be, what, 38 out of 50. And that's going to be 3. Okay, or you can use your binomial in the other. You can do 12C2 is 12 times 11 divided by 2, 6 times 11 is 66 times. You don't have to reduce the fractions, just put them in your calculator. Now, I didn't say what to round. Let's just go to 4 decimal places again, like we did in the last one. Okay, expected number of 6s. So expected value, the number of 6s. So the number of trials here that we're doing is 12. And the probability of getting a 6 is 12 out of 50. And then reduce that. 88 times, so around 3 times approximately. The variance of the number of sixes, so variance is basically the expected value, this part here, the expected value. And that was actually an exact value, so keep that. If it's not, if you rounded that, make sure you go back in your calculator. If it's there, and multiply by 38 divided by 50. Determinate, so just leave it. On an IB exam, they usually say, they call it 3 significant digits, but really it's not all digits. So 2.19. Okay, so probability that Vicky is home from school to watch the travel vlog live is 0.4. In a 5-day week, Vicky arrives home to watch the vlog on 3 days. Okay, so up to you which method you want to use. You can use this. That's 5 C3 0.43. I should say 0.6 squared. Okay, or final PDF 5, 0.4, okay, at least 3 days. You could go 3 days, 4 days, 5 days. Add them together. You could do 1 minus cumulative up to 2 days. Whatever you like. That's a little bit faster, maybe. The next one, you kind of have to think about it the long way, because 3 days which are consecutive. So please show the 5 days of the week like that. So that means we have to what's the probability that she'll be home to see it on the first 3 days, okay, or the middle 3, or the last 3, okay? So, probabilities will all be the same, and there's 3 of them. So you can say 3 times. So if you're going to see the blob 3 times, probability of that is 0.42, and not seeing it 0.6 squared. The 3 comes from the first 3 days, not from having 3 days, having 3 ways of having 3 consecutive days. Times 0.4 times 0.6. Okay, an expected number of, yep. Because this just says on 3 days which are consecutive. So that could mean that it's this day, and this day. That's one probability. It could mean it's this one, right? It doesn't say which 3 consecutive days. Yeah.
Because the other, like, the first 3 days, then would be, oh yeah, 5, 2, 3. But here it's less than that.
Okay, so then last one here. Expected number of days. So 5 days, probability of being home times 0.4. So expected number of days that you'll get home is 2 out of the 5 days. Standard deviation, so remember variance is the expected value times the complement of the probability. So the standard deviation is variance is standard deviation squared, so we've got square root of it. I didn't say what to round to, but okay, so there are some practice questions on the right-hand side. And there's more probability distribution questions on the last page of this. Remember, it's not a test on Thursday, so if you don't want to spend time looking at it now, maybe you do that over